Hey, it's good to see you guys today. I'm going to wait a little while, get you guys all in the course. Hopefully your internet is working. Hopefully my internet is working today. So, how are we all today? Looks like we've got a few people popping in. Happy Wednesday. Welcome to Gen Chem today. Get things all situated. Hi, Sterling. Hi, Mary. How is your Wednesday? It was, hi, Scott. It's Wednesday. Last week we had an exam. This week we're back to the usual. That means that your Alex will be due on Monday that covers this material. Hey, guys. Glad you're here today. As we get started, does anyone have any questions? I'm doing good. It's been really foggy and not really feeling the fog, but it's not cold, so I'm kind of happy about that. So glad you guys are all rolling in. Any questions? You should have already seen all of your exam feedback. Those were dropped on Monday. I feel like there's something else that I was like eminently thinking at you. I don't remember. So if you have questions, you can drop them right there in that comment box, and I'll answer those before we get started. I missed you guys last week. I'm so glad to see you. I mean, I saw you guys, but on Monday, and it didn't feel like the right day. So other important dates coming up. Mini exam 2 is on February 22nd. So not this week, but not next week, and something else. Muri asks what was the average, and as you may have seen, I don't provide that information. The average makes it feel like it's a competition, and it's not. And so whether you are the highest score or the medium score or the lowest score doesn't really change what it is. So I don't typically provide exam averages. But if you have questions about your exam, the key will go up hopefully this evening. If you have questions, feel free to send me an email, pop into office hours, schedule a meeting. I'm happy to chat about that. Let's see. Other questions, other things I need to know that you want to write in the public comment box? Oh, the internet here today is a little wonky. If you're on campus, you're aware of that. It may be a little glitchy. I'm plugged into a wire, not using the Wi-Fi, so hopefully that will help. But that's all we got. Any other questions? Otherwise, we will go ahead and start with question number 1. All right. So there are 4 videos for this week, chapter 4, part 1, 2, 3, and 4. And so those videos kind of are composed of some different things. And so we're going to start, I'm going to move this question down so I can actually see it, with some complete ionic equations. So in this chapter, the videos are a little stylistically different than some of the others. You'll see some that are the other style where I write on the paper. It doesn't look like very many people are watching the videos before we're coming to class on Wednesdays, so please make sure you're looking at those. So in this equation, it asks us to write the balanced chemical equation, the complete ionic, and the net ionic equation for the following reaction. And we're going to look for the precipitate. I posted the chapter 4 handouts. One of those is the solubility table. I will ask you which of these are soluble or insoluble based on that table. You should copy that into your notes so that you have it for the exam. It will not be part of your notes packets, but as it will also be an open notes exam, please make a point to get that into your notes. It's in the slides and elsewhere. the videos were stressful. Sterling, I would love to hear what you mean by stressful. Do you mean that they went quickly, or you know what? I'm going to look forward to reading about that. You are welcome to drop it in the comments box, or you can send me an email, and I'd love your comments on that. Miri asks, what happens if there's a solid on the reactants and products? So if you're asking, what do you mean if you dissolve a solid and get a new product, or if you can have no reaction where basically nothing occurs. You can also have a reaction where a solid is dissolved into a liquid and a different solid is precipitated. But in this case, oh, a lot is fine. I thought you were saying, anyway, I'm glad it's just a lot of info. We can work with a lot of info. The videos do get a little bit better, frankly, in my opinion, as the semester goes on. So hopefully they're going to kind of turn it into a little bit better. But in this case, we have a solution of barium acetate and magnesium sulfate are mixed together, and we're going to get a solid formed for this. So, one, the first thing we need to figure out is what is the chemical formula for barium acetate, and what is the chemical formula for magnesium sulfate. So barium is a 2+, and acetate is C2H3O2, which is a -1. So we're going to have two of these, which is going to be aqueous. We're going to add magnesium sulfate, also aqueous. So in this case, we're being asked to provide three different things. A balanced chemical equation. This is the same kind of thing you saw in chapter 3. This is just going to be a little bit more complex. So we have that, and then we're asked for a complete ionic and a net ionic. So a complete ionic is how we're going to figure out what the products are. So our complete is all of the different ions in solution. So each of these is going to break down into two parts. So we're going to have barium 2+, aqueous, plus in this case 2 C2H3O2 negative aqueous, plus Mg2+ aqueous, plus sulfate 2- aqueous. I'm going to get a better marker, or just maybe a different marker. So, in the complete ionic equation, we're going to look at all the ions. So, in this case, you should picture a beaker of water being poured into another beaker of water, and a fluffy solid is being formed. So the question becomes, what's going to be made? Now, in chapter 3, up until this point, I've always told you what's on both the reactant and the product side. Now, we're going to start to figure out for ourselves what is the reaction. Now, that feels overwhelming, and I got you. It turns out that the anions just switch partners. So, I got a blue marker for this. We're going to make a new compound of barium sulfate and a new compound of magnesium acetate. So from here, I'm going to rewrite those. Now we're going to add them as part of our complete, or our balanced chemical equation. So we're going to have barium sulfate, which is BaSO4. So we can check that the barium 2+ and the sulfate 2- are neutral. So we have barium sulfate plus magnesium acetate. And so it turns out that this equation is already balanced. Now, here comes the tricky part. Which of these two compounds is solid? So you get a solubility table, which I meant to bring a printout of and don't have. So the solubility table is either what is soluble or what is insoluble. in this case, when we look at that, it tells us that barium sulfate is solid. So this is a solid. Magnesium acetate is aqueous. So now we have a solid and an aqueous solution. Aqueous means that it's dissolved into its ions. Good news. So in the ionic equation, the number one place where students get a little bogged down is what do we see on the product side? When something is a solid, liquid, or gas, it doesn't dissolve into its ions. When you hear solid, it's like a rock. And the rocks, if you put it in a glass of water, don't dissolve into rock particles. Where if you were to take salt and dump it into water, it will dissolve to make salt water, right? When salt water is composed of sodium ions and chloride ions. If you're talking about ocean water, there's a lot of other stuff in there, but like just regular old salt water. So in this case, our barium sulfate is going to stay together. Because it's a solid. But I'm going to have to move that, magnesium 2 plus aqueous plus 2 C2H3O2 aqueous falls apart. So, what we got in our complete ionic equation, this is who is present, which is different than our net ionic equation. So the next one is our net ionic. Now the net ionic equation is a little different than the complete. The net ionic equation asks us who participates in the reaction. So in this case, anything that you see present on both sides in exactly the same way is going to get canceled out. So it turns out that we see the magnesium 2 plus ion. So I'm going to get rid of that. We also see the 2 acetate ions. So they're gone. So now our net ionic equation is only telling us what's actually happening. So in this case, we have our barium 2 plus aqueous plus sulfate 2 minus aqueous, and that goes to make barium sulfate solid. So, to recap, we have a pretty traditional complete ionic equation at the top. We were given this information and asked to determine who is the solid. We can do that by looking at the complete ionic equation. Now, you can try to predict the metathesis products by looking at this piece here and moving them around. You can do that. It will be a little easier if you go ahead and write out your complete ionic equation on the way to predicting your products. When you identify the solid, then it stays together on the product side. It does not dissolve back into its ions. The aqueous ion does dissolve. In this case, those two are canceled out to create our net ionic equation. So, what questions do we have about how this worked or about the process in general? If you don't have any questions, feel free to write none right in that comment box. Or you could give a thumbs up, or you could put an emoji in, or really anything. Next. These are easy once you, like Sterling says, you got to practice a little. We also want to make sure that we're spending a little bit of time to work out where things go. So Christopher and Sarah both are asking about how did you know to cancel? So these are great questions. So when we look at the complete ionic equation, we can cancel out anything that we see on the left that is present in the same way on the right. Those are called spectating ions. So a spectating ion is something that is present on both sides. And so the two things that are present on both sides, like the magnesium 2+ ion and, sorry, I'm not very good at this backwards stuff, the other magnesium ion are the same. So we can cancel those out. If you see something that is only present on one side or the other, such as the barium sulfate and the barium ion, you can't cancel those out because they're not present on both sides. So the acetate and the magnesium are spectating, and the barium and the sulfate come together to form a solid. So there was also a question by Daniel Herrera about how did I know which one was the solid? It's a good question. There is something called a solubility table. You can find that on Canvas in the handouts or in the chapter 4 slides that are also on Canvas. Or you can send me an email and I'll just straight up email you the PDF. In that table, there's also one, by the way, in ALEX. The ALEX one, in a non-shocking way, is like way more detailed than the one I'm going to give you. The exam questions will come from the one out of our textbook. ALEX just has more options on there. But it's basically for every anion and every cation, it's a double table on ALEX where it says, like, with sodium and chloride, is it soluble or insoluble? And insoluble means a solid. And so you can look at that table. The one out of the book, the top part tells you when it is soluble, and the bottom part talks about when it's insoluble. And I don't have a copy of it with me, so I can't actually show you how to read it. But in that case, that table is going to give you that information, and it tells you whether it's solid or insoluble. So Emma asks, you're just getting rid of the things that don't make up the solid. Emma, yes, that is totally correct. You are getting rid of the things that do not make up the solid for the net ionic equation. And so in this case, that is what's going to happen, and so we will figure that out. Glad to help. We're going to go ahead and do another example because, as we all know, practice makes better, I guess. So our next question has its own issues. So our next question asks, give the balanced chemical equation, the complete ionic equation, and the net ionic equation for iron sulfate plus lead chloride. So we have FeSO4 plus PbCl2. And so in this case, when you look at the solubility table, it turns out that iron sulfate is a solid and this is aqueous. So the question as written is very simple. There is no reaction. So you'll often see this in ALEX and sometimes in the book. We are going to work another real example. I realized after I'd both posted the slides and put them in the graphics. So in this case, because you start with an insoluble product, nothing can happen. Now sometimes you can dissolve something into it, like if you added solid sodium chloride to liquid, that would create a product. In this case, this is insoluble. Therefore, no reaction occurs. So before we go to a real example, let me tell you the other time when we're going to see no reaction. If we were to have sodium chloride plus lead chloride, which is not the best example, but in this case, when we create new products, they're going to be the same. So let's make this, sodium nitrate plus lead chloride. When we create the complete ionic equation, it'll be 2 sodium chloride plus lead nitrate. This equation, both of these are aqueous. And it turns out that all of these products are also aqueous. So in this case, you would get no reaction. Iron sulfate is soluble. I'll look back at that one. We're going to rewrite this problem no matter what and fix it. Or maybe it is fine. Anyway, we're going to do something different. So before we look at that one, because my notes say it doesn't work, but we're just going to ignore it. So if you put an insoluble product on the left, you get no reaction. If you have 2 aqueous solutions that make aqueous solutions on the other side, you get no reaction. And you can see that during the complete ionic because everything will cancel. So in that case, everything goes away and it's just a no reaction. Ordinarily, on any of my graded material, both the mini exam and the exam, we will not actually see anything where it doesn't work. It will always make a solid product. You will use the solubility table in order to look at that. So let's do a different example. So we're going to ignore everything up here. I'm just going to give you some other compounds. So if we have sodium sulfate, aqueous, plus lead chloride, also aqueous. In this case, we want to do the same thing where we determine the complete ionic as well as the net ionic equation. So again, the complete ionic is the dissolution of the sodium sulfate and the lead chloride. So we end up with 2 sodium aqueous plus the sulfate 2 minus aqueous plus lead 2 plus aqueous plus 2 Cl minus aqueous. From here we can determine our dos-to-do reaction or the metathesis where we're going to make lead sulfate and sodium chloride. So we're going to end up with 2 sodium chlorides plus lead sulfate from here, we are going to figure out which of these are aqueous and which of these are solid. So sodium chloride is aqueous, and our lead sulfate is going to be a solid. For the complete ionic, we're going to break these up into any ions that are present. We have 2 Na plus, aqueous, plus Cl minus, aqueous, Yahtzees. Just add a 2 in front of it. plus PbSO4 solid. A couple of things. You have to have a charge on everything that is charged. You also have to have a subscript telling you what the state is. These take a long time to write out. So all of these should have aqueous. If they're in fact aqueous, they should have a solid if they're solid. The other thing to remind ourselves is on the left, you should only have 4 compounds. Each complex should break into an anion and a cation. We don't tend to see any instances where the sulfate collapses into its atoms. Basically, I've seen students break it into the sulfur plus the oxygens. All of the polyatomic ions stay together. So in order to write our complete, net ionic, we're going to cancel everything out. It's on both sides. From here, we now have SO4 2 minus aqueous plus Pb2 plus aqueous gives us PbSO4 solid. Now, one thing you might notice is in the last problem, I switched these to where the cation was before the anion. It doesn't matter which way you put it. This, we name those or write the chemical formulas the way that we had before. In this case, it doesn't matter. It also doesn't matter the order, both on the left or the right, same up on the top. You can mix and match these parts provided all of your reactants live on the reactant side and the products live on the product side. So I know we went kind of fast, so let me move out of the way. So while we look at this type of a question, and so the question which is missing, the question would have been a solution of sodium sulfate and lead chloride were mixed together. What is the product? Or write out any given parts of these. So we're going to start with Dean's question. So Dean asks, could you go over the steps in the problem again? Happily. I'm happy to go over this again. So in order to answer this question, so I'm going to put back up question number 1 because we're just going to ignore the complexes at the bottom. So it asks us for a balanced chemical equation, which in this case, it's new to us at this point. We're being asked to determine what the product is, as opposed to last chapter where I just told you. I would just give you a bunch of compounds and ask you to balance it. So the balanced chemical equation is the first one. The complete ionic equation is basically showing which of these compounds break into ions. Any compound that has an aqueous, this AQ, means that it dissolves into its ions. So we saw this state first way back in chapter 1, 2, and more in 3 when we talked about reactions. So when we thought about that, it basically just said, hey, it means it's in solution. That means that when the sodium sulfate is added to the water, the sodium complex dissolves to where we have a sodium ion, well, 2 sodium ions, and a sulfate ion. Those 3 ions hang out in the water. The same is true for the lead chloride. We have a single lead and 2 chlorides. And in these 2 water glasses, they look like water glasses because they're both clear. When you pour them together, either it's going to still look like water with a bunch of ions in it, or you're going to get a product out. And so the whole point of this type of question is, what is the product? And so the way to figure that out is by going through the complete ionic equation to determine, okay, the anions are going to switch partners. So that's what these blue lines mean, which you may or may not really be able to see. So then we figured out what the products were. We then used our solubility table to figure out which of these is the solid product, which was here. So in the complete ionic on the product side, we write down the aqueous products and the solid. So you'll notice that the lead sulfate stays together. That is because the lead sulfate is solid. When it is solid, it is non-dissolvable. So this solid basically goes here. Then, in order to determine the net ionic equation, we're removing the spectating ions. Now, the spectating ions are any ions that don't do anything. It turns out that the sodium ion is present on both the reactant and the product side. So it's not involved in this chemical reaction. So we can remove that. And then we get the net ionic equation. Now, net ionic equations are really important in different types of chemistry. So in Gen Chem 2, you guys will use them a little bit more. So we're teaching you, where do they come from? It's basically saying that the lead ion that came from the lead chloride interacts with the sulfate ion from the sodium sulfate to create lead sulfate. This is what happens in this reaction, and everything else is just kind of present to hang out. Does that answer, did that give you more clarity, Dean? So Christopher asks, how do you find out what bonds to make a compound and what stays apart on the product side? So in this case, you will either have, you should have two ions that have switched partners, and if it is a solid, it stays together. If it is not, whatever complex ions you had on the reactant side will still be present on the product side. Is that what you're asking, Christopher, or are you asking something else and I just stated some facts? While we wait on responses, so we'll go ahead and move to question 3. Perfect. Glad I did, Christopher. So, Dean, feel free to chime in if you have other questions. So for our next question, I am going to, these are more mathy. Christopher, you are definitely correct. You just need to use the table. In the later chemistry courses, we can kind of predict other things, but that table's all you need. So our next question, number 3, asks, what is the molarity of a solution in molar when created when 12.5 grams of sodium chromate is dissolved in 750 milliliters of water? So molarity is the moles divided by the volume. No, moles divided by liters. So it turns out that we're given a mass in grams, so we got to convert that to moles, which we learned how to do last chapter. And we got a volume in 750 milliliters that we need to convert to liters. So the first thing I'm going to do is convert moles to liters. Nope. I'm going to convert grams to moles. Sorry about that. I'm going to take my 12.5 grams of sodium chromate and divide that by the molecular weight, which is 161.98 grams in 1 mole of sodium chromate. So that's going to give us 0.07717 moles. Now, I have expanded past the number of significant figures that I had. In this case, we're going to keep them around and then trim it back at the very end. Daniel, I believe that Alex is only over part 1, as Sterling says. So now we're going to convert the molarity, which is 750 milliliters. There are 1,000 milliliters in 1 liter, which gives us 0.750 liters. Then I'm going to divide the molarity, or the moles divided by the liters, which is 0.750 liters. And that's going to give us 0.10289 molar, which is on camera. And so from here, we need to pair back for our sig figs. So the question started with 3, so it'll be 1, 0, then we're going to round this, so we're at 0.103 molar. Okay, so what questions do we have about molarity? We've got a few more examples. Molarity is somewhat similar to density. This is how you determine the molarity. In some of the upcoming questions, we're going to use molarity as a tool. I'm not seeing any questions. If you have some, feel free to drop them in the chat. We'll just go ahead and drop the next question up so that if you did not work on it early, you can go ahead and start. If you have any questions, you can drop those. If you don't, we are going to keep on keeping on. Molarity is, I feel like I say this every week, like this is a top 5 topic. This topic is important. I consistently use it both in my research and in the other types of chemistry that I teach. We want to know what the concentration of a solution is that we create. And we're going to do that using molarity. Nice, Sterling. So number 4 is we are going to dissolve the concentration when 4.28 grams of nickel 2 chloride is dissolved in 150 mils. So in this case, it's pretty much the same calculation as we just did with new numbers. So we're going to take our 4.28 grams of nickel chloride. We're going to divide that by the 129.58 grams in 1 mole of nickel chloride, and that's going to give us 0.033030 moles. Again, I just kept some in there so that it can basically be a more accurate number. You can always pair it back here and then continue on. So we're going to take our 150 milliliters, divide that by 1,000, 1 liter, and that's going to get us 0.150 liters. Now, I show this step. You don't have to. If you know that you just need to move that decimal place 3 times over and drop it, that's equally acceptable and encouraged. I'm just showing it in case you're like, thinking about 2 things at once, and you're like, how did you get that? Please don't feel obligated to show this part of the calculation. It's not It is not essential. Then we're going to divide by our liters, which is 0.150 liters, and that's going to give us 0.2202 molar. And so we started with 3 sig figs, so we're going to need to convert this to 3. So our final answer is 0.220 molar. So what questions do we have? I'll go ahead and clear out number 3. Do we have questions about this calculation? It's relatively simple as long as we follow the steps. Convert to moles, convert to liters, divide the 2. So what questions do we have? Do we have any questions? If you have none, you can go ahead and drop none or an emoji or the letter. Any letter is fine. Nice, thanks. Thank you for letting me know. So now, in a pretty typical way, we're going to step up the difficulty of our questions. So this question says, calculate the volume in liters of a 1.1 molar sodium chloride solution that contains 175 grams of sodium chloride. This one came directly from Alex. Well, not directly. That would be rude. But it is modeled after some of the ones that you might see in your objectives this week. So in this case, we're not being asked to calculate the molarity. We're being asked to use the molarity the same way we used density or anything else earlier this semester. So we know that we have a 1.1 molar solution. We also know that we're going to add 175 grams to it. And so we're going to convert our 175 grams of sodium chloride using the molar mass of 58.44 grams in 1 mole of sodium chloride. That's going to give us 2.9945 moles of sodium chloride. So we're being asked for the volume. So we have the molarity and we have the moles, so we can just solve for the volume. From here, we're going to do a couple of things that at the beginning will feel a little complicated, but hang in there and we'll look at it again. So we're going to take our 2.9945 moles of sodium chloride, and then I'm going to use the molarity to convert to liters. So a 1.1 molar solution is also equal to 1.1 moles in 1 liter. Molarity, that big M, is moles per liter. So I'm just going to take the big M apart and make this calculation to where 1.1 moles in 1 liter can be used in this calculation. And so we can get 2.722 liters. And with the sig figs, because we need to pair it back to 2, it's 2.7 liters. So, what questions do we have both about this part of the calculation or about this part? How did we feel about this? Was it easy? Was it hard? What do we think? But it will be helpful if I would get out of the way. Let me go stand over here. gonna survive. Nice, I'm glad it's working out. Easier, it's really my favorite comment these days. Sounds like it's all good. I'm gonna give a little bit longer in case some people are still like, wait a minute. Nice, I'm glad you guys are getting the same answers. Molarity is, in my opinion, like a super exciting topic, so there's that. Yeah, Zach, that's exactly right. You're solving for a different variable in the same equation. This can work just like density. So Christopher asked, why was the 1 liter flipped? So I took this value and I wanted the ability to cancel moles in order to turn it into liters. So what the other thing that a lot of you like to do is to set up 1.1 molar equals 2.9945 moles in X liters. I find that this calculation doesn't always work. It will work if you track the X correctly. It is in fact the same thing here, where the 2.9945 moles is divided by the molarity. I just broke the units out so that I could follow the units through the calculation. And then I flipped it over so that I could determine how many liters there were in this calculation. I would have left it upright, and we're thinking about it that way, if I had been asking how many moles were in a 5-liter solution. Good question. I am going to reorder the worksheet, if you're looking at it. We're going to do the rest of the math questions, and then we'll go back and do some other equation questions. So we're going from 5 to 7. We will go back to 6. So now we're going to start to think about dilutions. Dilutions are everyone's favorite because we're going to get to use this fancy equation, M1V1 equals M2V2. So in this question, we have, what is the concentration of the stock of lactic acid when 75 milliliters of the stock is used to create a 350 ml of a 65 millimolar solution? So you at first might be like, oh, I'm gonna have to Google what lactic acid is so that I can convert to moles and figure this out. It turns out that we can use this equation called M1V1 equals M2V2. Where M is the molarity or concentration, and V is the volume. And it turns out that as long as the two molarities are in the same units, you don't have to convert them to something else. The same with the volume. If they're both in milliliters, you can leave them there. So M1V1 equal to M2V2 works really well as long as you assign the whatever is the stock together and whatever is the diluted part together as well. So in this case, in this problem, we're looking for the concentration. So M1, V1 is 75.0 milliliters, is equal to M2, which is 65.0 millimolar, times V2, which in this case is 350 milliliters. So if you cancel your units, your milliliters both cancel on both sides. So M1 is equal to 303 millimolar. we just read the problem carefully to determine which versions are the diluted and which is the stock. So how do we feel about this calculation? Did you get this answer? Did you find it easy? And what questions do you have about this? If you have none, go ahead and write none in the comment box so that I'll know. So Christopher asks, do you solve it like an algebra equation? Yes. So your calculation would be 65.0 multiplied by 350 divided by 75.0. So Mary asks, millimolar would be acceptable just like molar? Yes. In this question, it doesn't ask, so you could have converted it to molar or in millimolar. For me, both would be correct. Alex will usually tell you what it wants, as will I. I got a no from Scott, but I'm not quite sure what part of it you have questions about. We are going to work another 2 examples with this. So could you give a little, oh, never mind. I see that was just a typo. Thanks for updating. So let's look at number 8. So number 8 asks, how many mils of a 1.25 molar glucose stock are used to make 500 milliliters of 750 millimolar? So in this case, we have M1V1 equals M2V2. And so we know that our stock is 125 or 1.25 molar, but we don't know the volume. And we know that the solution is 750 millimolar and 500 milliliters. So we don't have to convert our concentration, but they're not in the same units. So we either need to convert 1.25 molar into millimolars or 750 millimolar into molar. I'm going to convert 750 millimolar into 0.750 molar because they just have to be in the same units. It's the only reason we made that small step. And so once we solve for this, we can calculate using algebra that 0.750 by 500 divided by 1.25 gives us 300 milliliters. This relatively large decimal point is 1, so it shows up on the camera, but to indicate that this value has 3 sig figs, just like all of the values we saw in our problem. Questions. How do we feel about dilutions? We have one more after this, but do we find dilutions to be easy, tricky? I don't know. Those are really the only options. What do we think? Do we have any questions? If you don't have any questions, feel free to drop that right in the comment box, and we'll move on to our last dilution example. Yeah. So Haynes asked, can you go over the conversion part? Sure. So the question said that we had 750 millimolar. And so in order for this calculation to work, the units have to be the same. And so I just needed to convert to 750 millimolar. There are 1,000 millimolar and 1 molar. And so that gives us 0.750 molar. So you could have also converted the 1.25 molar into millimolar, and you will get the same answer in this case. Pretty popular question. But yes, we were just doing a unit conversion in order to make these two the same units, which is something Alex is going to do for you as well. Other questions? Those are great questions. If you have more, keep them coming. I'm going to go ahead and put up question 9. A little bit hard to read. Yikes. Move that. I'm going to make 8 go away. Put that up here. So our next question, our last math question, and then we have a little bit more equation questions. Ooh, before we get there, T. Jizzle asks or states, can we do either? Yes. If you had wanted to, you would get the exact same number if you had set it up as, so now we're going to convert to millimolar. So 1.25 would turn into 1,250 millimolar times V1 times 750, I'm going to erase this, give us a little bit more space, times 750 millimolar times 500 milliliters will also give you a V1 of 300 decimal point milliliters. So it turns out as long as they are the same, it doesn't matter, and the answer will be the same. I feel like I said, if they're the same, it'll be the same. As long as your units cancel, you will end up in the right answer. If you try to divide two of the same unit, two different units, they won't cancel, and your answer will be off by a factor of whatever the difference is. But that's a great question. You could do either way. Great questions today. So our next question is, a chemist makes 780 milliliters of a barium chloride solution by diluting water to a 170 milliliter mark of a 37.4 millimolar stock. What is their concentration of the new barium chloride solution? This one, we're just going up to a whole different level. Pretty sure this one came out of the objectives for this week. If it's not exactly like that, it is very similar. Yep. We'll make sure. So we have M1 V1 equals M2 V2. So for our stock, in this side, we have a 37.4 millimolar solution, and we have 170 mils, and that equals our M2 times the volume of 780 milliliters. Sorry, I spaced out on that question. So then our molarity is in fact 8.15 millimolar. So this is an example of a problem where it's really important to follow the words. So this says that we're making 780 milliliters, so that's our total volume for V2, by adding water to 170 mils of a 37.4 millimolar stock solution. So our stock solution, we had 170 mils plus 37.4 millimolar, or multiply by this. We know this is the total volume. So the molarity of the new solution is 8.15. You should always see a stock, which is a higher concentrated, and a dilution, which is a lower concentrated, because we're taking a stock and diluting it into another. What questions do we have about this calculation? Did we find it easy? What do we think? How do we feel about it? Nice, Zach. Great. I'm glad that those of you who are dropping comments are saying it's pretty easy. We'll give another second to see if we have any questions, and then we'll go back to our neutralization question, which is the number 6 that we skipped a little earlier. So Sterling, when you say it backwards, do you mean that you put this version on the other side? Because it turns out that that's acceptable. And I don't want to say it also works. You can put the dilution on one side and the stock on the other and switch those, as long as the molarity and volume of the stock or dilute stay together on either side. So I'm guessing you did it just the opposite way. Sterling, that's also acceptable. If you guys look in the comments, she's shown basically swapped it around. Some days this time delay kills me. You did it exactly right, Sterling. So when we're all in the same place, it'll all work out. Any other questions? So our last questions of the day are to write the neutralization reactions. So the last thing we're going to talk about today is an acid-base reaction. So this is important because in the next chapter, well, next week, still in chapter 4, we're going to talk about acid-base titrations. In order to think about that, we kind of need to be able to picture what is a neutralization reaction. So a neutralization reaction is when we take an acid plus base, and we get salt plus water. It turns out that that's about the only products you get. A salt, which means an aqueous salt typically, and H2O, meaning water. So let's look first at HCl plus KOH. So we have HCl plus KOH. So we're going to look at the net ionic equation to help us figure out what the metathesis is. So we're going to have a split to where we have a proton, or an H plus Cl minus, aqueous, plus a potassium ion, aqueous, plus a hydroxide ion, aqueous. And so when we create these byproducts, right, this reaction where they swap partners, we're going to end up with KCl plus HOH, which is otherwise known as H2O. And so it turns out that KCl is a soluble salt, so we're going to get aqueous. And when we have water as a product, it's liquid. Now, liquid products are just like solids. They don't dissolve back into their ions. So, in this case, if you were to continue writing out your complete ionic equation, we'd have our potassium ion plus a chloride ion plus H2O liquid. And so you can write the net ionic equation, which I will write very tinily. You get H plus OH minus to give us H2O liquid. Not the best board work, but we're going to bring you guys a little bit closer so you could actually see what's happening. So the neutralization reaction is basically asking for this. What happens when you mix an acid, hydrochloric acid, plus potassium hydroxide, which is a strong base? We get aqueous potassium chloride and H2O. What questions do we have about this neutralization reaction? I'm going to go ahead and start erasing up here so that we can work on B next. Basically give us a little bit more board space since I wasn't thinking. But in our next example, we're going to look at sulfuric acid, which is H2SO4, plus sodium hydroxide, a different strong base. Okay, we've got some questions coming in. D to the first D asks, if it's not an acid plus a base, is it just no reaction? It wouldn't be a neutralization reaction. It would be a metathesis reaction or when everything cancels out. D, Jizzle, has a wait, excuse me, and so I would definitely love to hear your question. While we wait for his question, or their question, I'm going to continue to work on this one, but I will not erase this. So from here, we need to figure out what we get on the other side. So in this, sorry, I erased, I'll rewrite what I had erased in a minute. So we have aqueous sulfuric acid plus sodium hydroxide. We want to create a neutralization. So we're going to split this into our ions where we have 2H plus aqueous plus SO4, 2 minus aqueous, plus sodium aqueous plus the hydroxide ion, aqueous. So now we're going to create a do-si-do situation, where we have a sodium needs to go with the sulfate. In order to create sodium, our next product is going to be a sodium Na2SO4, and that is aqueous, which means that we're going to have to rebalance this equation. And then we're going to have H2O. But we need 2 sodiums here, so we're going to go ahead and add a 2 here, which means that has to be carried through into our complete ionic equation. And so we need to balance our equation looking like this. So the neutralization of sulfuric acid plus sodium hydroxide gives you sodium sulfate plus 2 H2Os, which you can't see because I'm standing in front of it. So our complete ionic equation would give us Na2, it would not give you that, 2 Na plus aqueous plus SO4 2 minus aqueous plus 2 H2O liquid. You might be like, oh. So it turns out that the net ionic equation for any acid-base neutralization, pretty much, is always going to be H plus OH minus goes to H2O liquid. And that's how a neutralization works. So let's try to move this out a little bit. Whoa. So that I can feel like I can stand in front of this and not be in front of the work. So that's what a neutralization reaction is. This acid plus base goes to a salt being an inorganic compound, and liquid water. That's all they are. So what questions do we have about neutralizations or molarity or anything else we've talked about today? If you don't have any questions, you can drop a goodbye in the chat, and I will see you next week or in office hours on Monday, Tuesday, or Wednesday of next week. Y'all have an excellent day, and I'm happy to answer any questions if you have them. And don't worry about asking me not to erase something you don't have to rewind. Then you might have a in-time question. I'm happy to answer those then. See you later, Zach. Have a great week. Bye, Sarah. Bye, guys. You guys have a great week. I'm glad you guys were here. It was good to virtually see all of you. Bye, guys. Ooh, there's an SI review session tomorrow from 1 to 2 if you'd like to work more problems on this. Have a great rest of the day. Y'all have a good one.